cool. Let's start this review. I know a lot of you are super excited about it. I don't know why. We're going to have two sections, as always, our general topics and then specific questions afterwards. I'll dismiss people who don't want to hear anything specific, and you can go home. And then we have normal, this will be posted on YouTube, barring no issues. And then if I ever refer to a video, you can check out my YouTube site. It's under my / normal site. And then the readers, but I guess it's maybe too late for those. And then if you're taking 2B with me or whatever, then I have the new readers out already. Okay, anybody here not from my class? Where? Okay, besides hearing from a friend, how did you hear about this?
Friends.
Oh, it's all friends. So you have there's a lot of nice people in our class, or mean people, depending on your perspective. All right, that's cool. Okay, I'm ready. I need you to raise your hand. Give me a topic that you'd like to come. Good. Stop. I'm only human. Okay. Oh gosh. Where should we start? Let's do a limiting reactant because that'll involve stoichiometry. Yeah. I guess those two. Okay. Limiting reactant. Start there. And I'll see, maybe I have an example here, I'm not sure. If I do, we'll do it. Okay. Limiting reactant problem. You want to be able to do these. There are 2 stoichiometry problems in a row. And we want you to be able to not only recognize it, you recognize it when there are 2 or more reactants that lead to moles. Okay, so information about 2 more reactants that lead to moles. Let me see if I might have one in here, and then that would be pretty handy because then we could just do that. Okay, let's see. We have, here's a pretty typical one, Cl2 plus 4NaClO goes to 4NaCl plus 2ClO2. We have 1 liter of Cl2 at 10 degrees C and 4.66 atmospheres. That's reacted with 0.750 liters of this and 0.200 moles, and then 25.9 grams of the ClO2 is collected. I want to know the percent yield. Oh, this is all, I don't know if somebody asked me percent yield, but if you did, here's the answer. Okay, here's a pretty typical question. This would be a limiting reactant problem. Here's how I know that. I know information that leads to moles about more than 1 reactant. In this case, 2 reactants. And I can use that to find the moles or mass of the products. In this case, we're interested in ClO2. Now notice they already gave me a mass. When they give you a mass, they're basically saying that's an experimental mass. So that's not what you would calculate. So we want to calculate the mass. We should get an answer bigger or smaller than that. If I calculate using information on the left, will I get a number bigger or smaller than 25.9? It should be larger because the percent yield, you're always going to get less. Good to ask now, right? Okay. So I should get a number bigger than this because this is my actual, and remember it's actual divided by theoretical, what you calculate, times 100. And this is less than 100%. So the actual must always be smaller. Okay, so let's try this. Okay, so for this is going to be awesome. Because to get moles, notice usually they would give you mass or moles. But in this case, I have a volume, I have a temperature, I have a pressure. We're going to use the ideal gas law, PV over RT, to calculate this. And we're going to get the moles of Cl2. P, 4.66 atmospheres times the volume, 1.0 liters, divided by R, 0.08206. That'll be given, and then T, 10 plus 273 to change it to Kelvin. Okay, let's see if I have, that's the moles of Cl2. I have that number. It should be around 0.200 moles. Okay? And that's of the Cl2. Now I want to use that to calculate the moles of the product of interest. That's the ClO2. So I'm going to take the 0.200 moles. That's of the Cl2. And then I'm going to say, well, there's 2 moles of ClO2 for every 1 mole of Cl, just from the coefficients by balancing. And so this is just going to double it. You get 0.400 moles of the product ClO2. Okay, there's half of it done. Now I have to do the exact same thing for the other reactant, but now I've got different information given. I've got molarity and volume. I can't use the ideal gas law in this case. I'm just going to use conversion. So, in this case, for the second one, this is the NaClO, that one. I'm going to say, well, 0.750 liters of that times 0.200 moles per liter, and notice the liters will just drop out. So this one turns out to be a number. What is this number? Is it 0.15? Is that right? Moles. And this is of NaClO. Now I want to do the same thing. Now that I have moles, I'm going to convert to moles of the product. So again, this is moles of the reactant, 0.15 moles of NaClO. I'm going to take this and say, well, from the reaction at the very top of the screen right now, there's 2 moles of ClO2 for every 4 moles of NaClO. By the way, what's the name of this? NaClO. Sodium hypochlorite. Yeah. This equals, I'm going to basically divide by 2. Hopefully I've done this right. I don't know. Oh. This is, oops. Whoa. There's a dot here. It's 2. Get your eraser out. Okay, so this is going to turn out to be 1.5 actually. Miscopied. 1.50. So this is going to be 1.50. And so we're going to get 0.75 moles of ClO2. Okay, which one's the limiting reactant? Cl2? Well, the top or bottom? In this case, the one that gives the least amount of moles, and that'll be the top one here, and that's from the Cl2. So Cl2 is our limiting reactant. We produce 0.4 moles of the ClO2, and now let's find what they asked for, the percent yield. Okay, to get the percent yield, I wrote down the formula already. The percent yield is going to equal the actual 25.9 grams. And now what number am I going to put down here? I have to do one step of calculation. I have 0.75 moles of Cl2, but I need mass of ClO2. So I'm going to go 0.7 up, 4, easy. You guys are excited. And let's see if I have the molar mass handy here. It's 67.45. 45 grams per mole. By the way, that's going to turn out to be 26.98, which is bigger than the number given, which is what we expected. Okay? So this bottom denominator turns out to be 26.98. It's larger than 25.9. That's good, because the percent yield better be less than 100 and bigger than 0. And it turns out to be about 96%. Okay. Any questions on this? This was a tougher one, but includes all the pieces of a fairly normal limiting reactant problem. Questions? Yes? Oh, if you were asked, a common question that this one didn't have is how much sodium hypochlorite would be remaining when the reaction has gone to completion. So let's try that. That's a fair question. So again, the one in excess is the NaClO. I started off with 1.5 moles of NaClO. How much of, not all of this is used up during the reaction because it's the one in excess. So what you can do is find how much of this is actually used. It's going to be a number less than 1.5 moles. So to calculate that, you would take the actual answer of moles, this is how I do it at least, of the product, moles of ClO2. Take the actual answer. And then what you're going to do is convert back to this sodium hypochlorite. So using the formula from before, there's 4 moles of NaClO for every 2 moles of ClO2. So I'm going back to the one that was in excess. This is going to turn out to be 0.800 moles of NaClO. And you can see 0.8 was used, but we were given 1.5. So we didn't need all of the 1.5. To find the moles remaining of NaClO, you would just say that equals the amount given minus the amount that you actually used. So it'll be somewhere around 0.7 moles of NaClO extra. That was remaining that did not react. Again, pretty typical limiting reactant type question. Good. Okay, next, let's move on. No time. Okay. Let's see, we gotta get back to watch the finale of The Bachelor. Okay. So, gas law, is it open? Okay. It was Juan Pablo, right? Yeah, poor guy. Okay. Since I have the gas laws up there, let me say a little bit about gas laws. I would put them in these kind of categories. There's the ideal gas law, and then there's the ones that have an initial and a final state. So those would include like Boyle's law, Charles' law, those sort of things like this. Or if you're in my class, I just think of the combined or general gas law, which would be this, which combines every single one of the gas laws, where there's an initial to final state of change. There's those are the ones where there's a change. Then there's Dalton's law. Dalton will use its own law plus P total is P, say, of component I plus partial pressure of component J, all the way up to the total number of components. The mole fraction of I plus the mole fraction of J and all the components in there equals what number? 1. That's exciting. And then the same with the moles. The moles of component I plus the moles of component J plus all the moles equals the total moles. Okay? Those are generally the equations that you would use. By the way, the mole fraction of I individually in terms of moles would be the moles of I divided by N total. You typically use that, and then I would also be using the ideal gas law if it was me, if you solve it via my style, where you can have totals here, or partial pressure of component I times V total equals the moles of I RT. Okay? So all those go together as a set of gas laws for Dalton's gas law. Okay? So we have all these so far. Let's go to the next one. Another set of gas laws that you'd want to be familiar with is Graham's law is kind of a gas law, where you would generally go the root mean square velocity of, say, component I over the root mean square velocity of, say, component J is the square root of molar mass of J over I. Okay? So there's Graham's law, and I think that covers pretty much all of the gas laws. I might be missing one or two. But so you basically just want, when you, and this is, our question was, what's the general concept of the gas laws? Basically what I would do is figure out what type of problem you have. So if you have more than one component in the mixture, then you either have a Dalton's law, the lower left, or it's a Graham's law, which is the one on the right-hand side that's vertically written right now. So it's one of those, if you have more than one component, more than one gas, you know it's a Graham's law if they ask you about things like the root mean square velocity. You know it's Dalton's law if they ask you about partial pressure, total pressure, anything like that. And then you know it's one of these sort of questions if something changes in the reaction for a given component. Okay, so that's how you would tell the difference. And I think that was a question that somebody asked me about gas laws. So that was just general concept for gas laws. I think the main thing is to figure out which one you're using. Thanks. Which one you're using, so use the right equations. Okay, let's move into now, let's do a couple of these. Let's do a redox. Okay, I think I have a redox question handy. Let me see. Yes, ooh, I have a tasty one. Okay. All right, redox. S2O8 2 minus plus FeCN6 4 minus goes to S plus FeCN6 3 minus plus H2O. And the question is balance it. Which one's oxidized, which one's reduced, and balance it in acidic conditions is what it's asked for here. Okay. So this is your typical redox reaction. Anybody know what I'm going to do with the water? I'm going to ignore it because it adds back in step 2. So I don't need it because if I leave it in there, I'm going to have to guess what side do I put it on or what half reaction do I put it in. That's too messy. So just ignore water or H plus or OH minus if it's ever given in the original reaction. Okay, so now let's separate these out. We've got S2O8, 2 minus, goes to sulfur, and then the other one, let's do the other one in a different color. FeCN6, 4 minus, goes to FeCN, also 6, but 3 minus. Okay, let's get the charges and all that stuff on here, or the oxidation states. I'll do the easy one, this is 0. Okay, sulfur right there. What's the oxidation state? Okay, I'm ready. I got it. Plus, yeah, I like that. Plus 7. So 7 times 2 is 14. This is minus 16 plus 7. Okay. Ooh, this is a good one. Iron right here. What is that? Okay, I'm ready. I got plus 2. Thus, this one is plus 3. Do I need to do any of these? Which one would you like me to do, if any? Which one? The iron one? Okay, if you were doing the iron, let's do that on scratch paper here. If you're trying to figure out what the oxidation state of iron was, say you got iron, CN6, 4 minus, what's the charge of CN? -1, that's one of your polyatomics. So you've got an iron plus 6 -1s equals a -4. 6 minus 1 is for 6 cyanides. So iron minus 6 equals negative 4. And now we're to like 6th grade math here. So add 6 to each side. 2. So the first one's 2. The second one, you do the same thing to get 2. Okay? Is that cool? Okay. If you can't do it in your head, or you're afraid you'll make a mistake, please do it on paper. All right. So let's balance. Oh, which one's oxidized?
Iron.
Iron is oxidized. Which one's the reducing agent?
Iron.
Also iron. Okay. Cool. Make sure you know those terms and how to identify them. All right. Let's do sulfur. No, let's do the iron first. Iron's more fun. So, step 1, I'm going to balance anything that's not oxygen or hydrogen. That's the same on both sides right now. Step 2, balance oxygen. There is none. Step 3, balance hydrogen. Is none. Step 4, balance a charge. So I'm going to put an electron where? Right or left? Okay, now it's a negative 4 on both sides. That one's balanced. Okay, let's do the other one. Step 1, balance whatever is not oxygen or hydrogen. That's sulfur. 2. We need 2 sulfurs there. Step 2, balance the oxygens with water. There's 8 here, so I'll need 8 H2O. So now there's 8 oxygens on both sides. Step 3, balance the hydrogens. There's 16 over there, so I need 16 H pluses. Now there's 16 hydrogens on both sides. Okay, right now the overall charge on the right-hand side is 0. How about the left-hand side?
14.
It's right now plus 14, 16 minus 2. So I need how many electrons over here? Yeah, 14 electrons. That'll make the overall charge in the first reaction 0 on both sides. All right? So I'm ready to put these together. I'm going to multiply the top by 1 and the bottom by 14. That because the electrons need to cancel. All right, so I'm going to get, oh my gosh, 16 H plus S2O8 2 minus plus 14 FeCN 6 4 minus. Okay, I think I got all the reactants. Now let's do all the products. We got 2 sulfurs plus 8 H2O plus FeCN 6 3 minus. Oh, did I miss something? There's 14 of them. Okay. Cool? I think, and it's simplified. We're good. That's the final answer. If you had to move this to basic conditions, what would we add? Hydroxide, and there would be how many? 16 to match the number of H pluses. Okay? All right. There's your balancing. Let's cross that off the list here. And it is serendipitous. I already crossed it off. Shoot. Okay. Rydberg happens to be on the same page here. So let's do a Rydberg example. Yes? Do you need state symbols? In this question, they didn't ask for it. But if they did, aqueous, 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 liquid, solid. Yeah, good. Okay. But this question didn't have to ask for that. Okay, let's do, yes? Hi? The water came back magically. There was 1 here, but it wasn't balanced. There should be 8. So there should be an 8 in front of this. Originally, you do not add it back. You throw it in the garbage or the recycling. Okay? All right? And there was supposed to be 8. The reason is you might have put it here wrongly. And that would have messed up your balancing. It wouldn't have been the end of the world, but it would have been easier if you just ignored it. Okay, what was it going to do? Rydberg. Okay. What is the wavelength? Hey, somebody asked me about wavelength. It's the length of 1 unit of a wave. Okay, that was the answer to that. That's a wavelength. It's the length of 1 unit of a wave. For example, this, that would be a wavelength. It's actually literally a length. so it's in meters or nanometers, things like that. What's the wavelength of a photon released from a hydrogen atom when dropping from the n equals 5 to the n equals 2 energy level? Okay, and this is for hydrogen. So the Rydberg equation has energy equals the Rydberg constant times 1 over n initial squared minus 1 over n final squared times z squared. Okay, and then energy is h nu or hc over lambda. This is going to be helpful because lambda is what we want, and we have everything else. We have z, Rydberg constant, and we have the two n values. So we're going to use this equation. Let me rewrite it now. The Rydberg constant from the back of the test would be 2.179 times 10 to the minus 18 joules. 1 over n initial squared, what's that number? 5. It started at 5. Minus 1 over n final squared, 2. Z, what's z? I know it's an atomic number, and that number is? For hydrogen, it's 1. Okay, so it's the higher red number on the periodic table up there. That equals hc over lambda, h, oh wow, I don't have enough space, equals h, 6.626 times 10 to the minus 34 joule seconds, times c, 2.9979 times 10 to the 8th meters per second, all divided by lambda. You're solving for lambda. It turns out that lambda in nanometers is going to be 434. This would be a good example when you get home, or if you're bored right now, to see if you can calculate this number. Okay, make sure you can do this kind of math. Let me do a slightly alternate question, because this will knock out ionization energy. Okay, ionization energy, and this is chapter 8. There's two common ways to calculate ionization energy. Okay, one common way, well, I'll do that in a minute. Another common way that we're not going to do, if you're given the ionization energy values, like there was an example on my homework just like this, where you're asked about silicon, and for a silicon atom, you're asked to find the ionization energy. Let me write that out. So we'll come back to this question in just a second. On the homework, there was silicon, and silicon for the electron configuration is neon, 3s2, 3p2. And the question on the homework was find the ionization energy total to ionize all n equals 3 electrons. Okay, and n equals 3 electron, well, that would be all of these, because n is 3 for 3s, and n is 3 for 3p. So how many total electrons are we talking here? 4, 1, 2, and then 3, 4. So the total ionization energy, if you want, for all n equals 3 would be the, that should say 1. Ionization energy for the first, plus the second, plus the third, plus the fourth. And all of these 4 would have to be given. Okay? So all 4 of those would have to be given, and you can solve for the ionization energy by merely adding those numbers. Okay? That is a way that you've seen in the homework. By the way, which value, 1, 2, 3, or 4, would likely be the smallest? 1, the one that loses the first one, probably. The first electron lost is usually the easiest to lose. Okay? Would the fifth, if we did the fifth, would the fifth ionization energy be larger or smaller than 1 through 4? It would be larger because you're removing what kind of an electron? A core electron. What are these electrons called? Valence electrons. You know it's a valence. You know what a core electron is because it's whenever there's brackets and a noble gas, all the noble gas electrons are core electrons. Anything written after the noble gas is called a valence electron, and those are easiest to remove. Would I5 be significantly larger or just a little larger than 4? Significantly larger because it is a core electron, it's very hard to remove. Okay? So that's one way the ionization energy works. Let's show you the second way now. And it's going to refer to that problem we just did. Let's say we had that photon on the n equals 5 level again, but now we ionize it. And then I want to know what's the energy. We'll just do energy. You could do wavelength if you want, just like the previous, but let's just do energy. Well, to do that, let me write the Rydberg equation again. Okay, there's the Rydberg equation all over again. Let's zoom in on it so you can see it easily. Okay, what's n initial? 5. What's n final if it's ionized? It goes to infinity because it's going to the infinite orbit, which is not even on the atom. So n final goes to infinity, n initial is 5. That's where it starts. So when we write, and this is ionized, so we're calculating an energy called the ionization energy, you'll see this in chapter 8 written like this. The Rydberg constant, just times 1 over n squared, that's the n initial squared, and then times z squared. It'll just look like that. Okay. So just for this problem, what you would do is you go, the ionization energy is 2.179 times 10 to the minus 18 joules. That's RH. 1 over n squared, that's 5 squared. And then, what's z for this problem? Same as the last time, it's 1. We're doing it for hydrogen. Okay, so this is for hydrogen. So here's how you do it. Okay, by the way, I'm removing an electron. Is this going to be a positive or negative number? I should get a positive number. I'm putting energy in to remove an electron. In the previous example, that was this one. In the previous example, would this be a positive or negative energy? You should get a negative because it's going from a higher to a lower orbit, 5 to 2. So energy is being removed in the form of light, and specifically 434 nanometers. Okay? All right, cool. That's enough with Rydberg and ionization. We tackled 2 just now. That was awesome. I crossed off Rydberg. Let's do I also. Okay, let's do now. Oh my gosh, there's so many. Let's do some quantum numbers. Okay, let's do quantum numbers. Couple different types of quantum number questions we could ask you. One would be, is this allowable? Yes or no? You should say no, I hope. And because why? Yeah, because n, this number right there is 3, and L is the letter F, which is 3. Now, if L is 3, is this one okay? Yeah, so this is not okay here, but if L equals 3, M sub L could be minus 3. Can M sub S be minus 1/2? Yeah, that's okay too. All right. Another common question, let's say n equals 3. How many in M sub S, let's say M sub S is minus 1/2. We want to count how many total electrons this could encompass. How many total electrons can have those 2 quantum numbers? All right. Well, if n equals 3, L could be, what's the largest L could be? 2, and 1, and 0 are the possible values for L. So M sub L, I'll put it up here, kind of like a little table. M sub L for 2 would be 0 plus or minus 1 and plus or minus 2. For 1 would be 0 plus or minus 1, and for 0 would just be 0. Okay? So, how many total orbitals are there right now? many total orbitals are in this situation right now? Not 5. Should count 9. I did, at least, I think. This is 5 here. There's 5 from this one. There's another 3 from this one and 1 from this one. That's 9. I'm counting just the number of digits. A 0, a +1, -1, +2, -2. And a 0, a +1, -1, and then a 0. So I'm counting a total of 9 values of m sub L. The number of values of m sub L equals the number of orbitals. Each orbital, each of those 9 orbitals can hold how many electrons? 2. So each of those 9 can hold 2 electrons, and one of them will be spin down, -1/2. So how many electrons could have these 2 quantum numbers? 9. How many are total in the n equals 3? That would be 9 times 2 or 18. Half of them, 9, are spin up, and the other half are spin down. They only asked us about the spin down, -1/2, so that's 9. Any questions on that?
Yes.
Repeat that. Okay, the total number, if for n equals 3, the total number of electrons that could be there is 18. Why? Because there's 9 orbitals, and there could be half, each can hold 2. 9 times 2 is 18. Half of those 18 are spin up, and half are spin down. So each orbital can hold a spin up and spin down. So a total of 18, 9 of them are spin up, but they ask us about the spin down -1/2, so that's 9. Okay? Uh-huh. Yes, hi.
Explain why the first one doesn't make sense, because if f is 3, can it go from like -3 to +3?
Yeah. Oh, if L is 3, this one?
Sorry,
Yeah, that's fine. That's okay. So this and this are okay. This, and this are all cool.
Okay.
No problem. This is the problem, the 3 here. N must be larger than L.
Oh, I see. Okay.
So it has to be 4F, or if it said 5F, or anything like that, it would be fine.
Okay,
But
thank you.
yeah, 3, 2, etc. would work. All right. Those are a couple quantum number questions. I'll skip the electron configurations. I hope you can do that. Nobody asked me anyways. Let's move on to the new stuff. Let's do some Lewis craziness. How about that? And I had a tough one for us to do. So let's do that, if I can find it. Yeah. Maybe we'll do a warm-up, not tough one first, and then we'll do a tough one for Lewis. Okay. You're given, here's an A question, you're given the molecule H2NOH. Question 1, draw the Lewis structure. So you go valence electrons, equal. There's 3 hydrogens in column 1, there's a nitrogen in column 5 and an oxygen in column 6. It's 11, 12, 13, 14, total of 14. And they give you the structure essentially. There's H and an H, an O and an H. Okay? Zoom in on this a little bit. And then, so 2, 4, 6, 8. Just drawing single bonds, I've used 8 of the 14 electrons. The next set of electrons we're going to put where? Yeah, outer, but they all are hydrogens, so that won't work. Oh, yes, that sounds great. 2, 4, 6, 8, 10, 12, and then let's do the nitrogen, 14. Everything has an octet. Okay, what's the formal charge on all the hydrogens right now? 0 nitrogen.
0.
0 oxygen. 0. Do I need to do any of those for you? I can if you want. Okay, that was the silence, so I assume no. All right, and then we did the formal charges. Let's do the shapes now. Vesper. So let's start with this one here. E.g., the electronic geometry is tetrahedral because it has 4 groups. 4 groups means tetrahedral. The molecular geometry with one lone pair is called trigonal pyramidal. Trigonal pyramidal. Over here, the electronic geometry for 4 groups, also tetrahedral. But the molecular geometry is bent. What are the bond angles? They're all 109.5. Okay? As the ideal bond angles. So now let's draw it. If they asked you to draw it, I would assume, unless told otherwise, to draw it to the correct shape. Okay? So let's try that. For the nitrogen, here's what a trigonal pyramidal would look like. This is all in the reader if you need that. Oh, there's only two hydrogens. And then oxygen is bent. It would just look like that. So that would be the structure that you would draw. Okay. Is it polar? Yes, definitely polar. It's asymmetric looking, so it has to be polar. Anything that's asymmetric looking will be polar. What's the hybridization of this nitrogen right there? sp3, because there's 4 groups. And this is sp3. If you're not that good with hybridization, let me do a little summary for you. All you do is count the groups. 1, 2, 3, 4, 5, or 6. And then you assign a hybridization. First one's S, not technically hybridized. The second one, because there's only one s orbital, has to add a p. Then the next one has a p2. Then 4 groups, sp3. Now we're out of p orbitals, so now we start adding d's. sp3d and sp3d2. Okay? All right, so these both have 4 groups, so they're both sp3. All right, let me see if there was anything else for that one. How many sigma bonds are here?
Question.
Oh, okay. While you think about that, I'm going to sigma and pi are the next questions. Yes.
Can you actually go over the formal charges?
How do I do the formal charges? Anyone in particular, or whatever?
No. Yeah, whichever.
Okay. So for nitrogen, are you in my class or different?
No. I'm in Tubagakis.
Mine is different than your instructor, so you need to choose a way. Okay, this is my way of doing it. Nitrogen is in column 5. Is that cool?
Yeah.
It's in column 5, and now you can count the number of things around it. So go up here. 1, 2, 3, 4, 5. It's even. Do it for oxygen. It's column 6 on the periodic table. 1, 2, 3, 4, 5, 6. Even. 0. And in fact, if you were ever going to guess, if you didn't know, you're going to guess a formal charge, what would you guess? 0, always. Maybe 80% of the time, it would be 0. Yeah. Okay?
Thank you.
Okay. What was I doing? Sigma. Yes. Yeah, the oxygen looked like, say, this. This would be 1, 2, 3, 4, 5. It's under by 1, a negative thing, so it's a plus 1. If it looked like, I can't think of that. Oh, if it looked like this. If it looked like this, 1, 2, 3, 4, 5, 6, 7, it's over 1 negative. It's a minus 1. Okay? This, you can also look on the end of that chapter of my reader. It has kind of some typical ones. Yes? If it doesn't if it's asking for a drawing, I would assume it means the 3-dimensional picture, always. Unless told otherwise, you're safer doing this. Okay? All right. How many sigma bonds? Yes, 4. 1, 2, 3, 4. How many pi bonds? None. There's no double or triple bond, so that's 0. Okay, let's try a harder one. And we'll do the same thing for this one. Sigma, pi, hybridization, whatever. Okay. This one gives you a structure I5 minus, but it tells you the shape looks like a V. So if you draw the structure and it ultimately does not look like a V, you have the wrong answer. Okay? So let's try this. I5 minus. Well, the valence electrons, there's 5 iodines in column 7 plus 1, that'll be 36. Okay, I should not do this, and you can tell me why. Why would I not do a shape that looks like this? There's no way this could ever look like a V, okay? So, you need to go back to like kindergarten, and remember, okay, V, it has to be somewhat linear looking, okay? 2, 4, 6, 8. There's my skeleton. 8 of 36. Let's fill this craziness in. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Remember, we do the outsides first. Now let's do the octets in the middle. I forgot what I was at. I was at 20, 22, 24, 26, 28, 30, 32. I have 4 more electrons, 32 of 36. Where do you want to put those 2 lone pairs? You want to put them all on the central atom. Is that what you want? By the way, there's 3 central atoms. So which one? The center one. All right. Okay. First of all, let's look at this one right there. How many groups? 4. So that is called what electronic geometry? Tetrahedral with 2 lone pairs is called bent. That's bent. What's this? Also bent, right? Same thing. This, it's not even taught to you. So 6 groups is octahedral, but you don't know what 6 groups with 4 lone pairs would be. So it doesn't even exist in chemistry 2A. So right now you have a structure that's like this. That is no way looking like a V to me. Okay? So that cannot be it. Okay, wrong. Do it again. And that happens sometimes. You try it, and it's not the structure they were looking for. So we were here. I'll draw where we were. Okay, where do you want those extra 4 electrons? Okay, I heard one person say, one here, right? And then another one here. Okay, we can try it. If it's wrong, we'll laugh at you and then we'll move on. That's cool. It's cool, right? It's cool. Okay. So, this one here has how many groups? 5. 5, what's electronic geometry? Trigonal bipyramidal. 5, with 3 lone pairs on 5 groups, what's that called? Linear. That's nice. Those are both linear. Let's do the center one. The center one has how many groups? 4, just like before. That's tetrahedral, 2 lone pairs, that's bent. Hey, that sounds like a B to me. Yes! Okay, so it would look like this. And they tell us the experimental bond angle is 95. What would be the ideal bond angle of this species? Well, if it's tetrahedral in the middle, then it would be 109.5. Okay? You would put brackets around it because it has a -1 charge. Now, let's do the formal charge because you all are into that for some reason. Okay, right here, what's the formal charge of that one right there? That iodine, kind of in the middle of the VR. Yeah. I got, actually somebody told me, -1. Why? Because iodine's in column 7 on the periodic table, and I count 1, 2, 3, 4, 5, 6, 7, 8. It's 1 over. It's a -1. How about this one? You get a +1. It's in column 7 again. 1, 2, 3, 4, 5, 6. It's short by 1. And this likewise would be -1 like its cousin over there. How about either one at the end? Would be 0. There's 1, 2, 3, 4, 5, 6, 7. It's in column 7. Notice the sum of the formal charges always equal what number? The overall charge. By the way, what's the sum of the oxidation states always equal to? Sum of the oxidation states. Also equals the overall charge. Both. Okay, that's B. Oh, let's do the hybridization. That'll be exciting. Okay, what's the hybridization of this one right here? Right there. sp3d. Same as this one, sp3d. And this one right here in the middle. sp3. 4 groups, sp3. How many sigmas? There's no pi's. Huh? 1, 2, 3, 4. I'm just counting bonds, literally. 4. Is that okay? Okay. Polar or non-polar? Is it symmetric?
Yes.
No. This would be symmetric. And X would be symmetric. There's iodines on top and not on the bottom. It's symmetric, you're right, this way, but not this way. And think about back to the reader on a tetrahedral bent. Is a bent ever polar? No, I should have said is a bent ever non-polar. Is a bent ever non-polar? That was a backwards question, which you all got wrong. Is a bent ever non-polar? No, it's always polar. Bent things are always polar. Okay, so this is polar. It's asymmetric. Even though they're all iodines, it does not matter. Even though it's symmetric with respect to the V, it doesn't matter. It's not symmetric this way. Okay. All right. Wow, we're running out of time. I did a lot of the Lewis stuff. I did almost all the Lewis stuff. Let's do an MO diagram. Okay. Somebody over here, an atom. Carbon. Pick a charge.
Follow me.
I don't like any wounded flesh. Okay? So that comes from 2 carbon plus 1. You draw the molecule in the center, the atoms on the outside, and then you draw this energy scale here. Carbon plus 1 would be 1s2, 2s2, 2p1, right? 1s2, 2s2, 2p1. All right? And then you draw each atom. You don't have to draw the 1s. Why not? It's called what kind of electron? A core electron you can ignore. 2s and then 2p. So I'm not drawing the 1s. And then over here on the other side, 2p, 2s. Okay, every bond has how many parts? 2. A bonding and an anti-bonding part. So you come down here to the 2s, there's a bonding and an anti-bonding part. Okay, there's that part. And then you go up to the 2p, you have to remember, in this example, because it's carbon, anything from nitrogen or to the left will follow the pattern 2, 1, 2, 1. So let me draw that. 2, 1, 2, 1. Okay. So this is the pattern for nitrogen or to the left on the periodic table of 2, 1, 2, 1. Okay. Now let's name these. Anything with a single line is called a sigma. So these are all going to be sigmas. Sigma, sigma. Easy. With a double line, it's a pi. The subscript is where it came from. So the bottoms are 2 s's. They come from 2 s's. The tops are 2 p's. They come from 2 p's. And then anything above, the higher one, is always with an asterisk, meaning antibonding. It's an antibonding part of the bond. The ones on the bottom, the low energy ones, are bonding. Okay, now let's fill in the electrons finally. 2s2, so 2s2 on each side, and then 2p1. So put 1 in the 2p's. 2s2, 2p1. Now let's fill in one set at a time. For the 2s, There's 2 on each side, or a total of 4. So 1, 2, then you go to the top, 3, and then 4. And then for the 2 P's, there's only 2 of them. So 1, and then not paired, 2. Third one would pair. Okay, let me get another color out. Para or diamagnetic? This would be paramagnetic. Because you look in the center, if you see 1 or more unpaired electrons, it is paramagnetic. If they are all paired, it's called diamagnetic. Dia for 2. Okay, bond order. I recommend always looking at the top picture. What's the first number? 2, because there are 2 electrons in bonding molecular orbitals. And the second number is 0, because there are 0 electrons in anti-bonding molecular orbitals. So this is 1. Okay, that would be a single bond. And that would be a pretty typical MO diagram question.
Question.
Yeah.
Why is the electron configuration 2p1 and not 2p2?
Why is it 2p1? Because it's carbon plus 1.
Okay.
So that'd be like boron.
Thank you.
Yeah. So that's why it's only 1. Normal neutral carbon would be 2p2. Yes, hi.
Is there more than one way of doing this?
I don't know another way of doing it. Do you know another way? Are you in a different class? Maybe that's the first question I should. Are you in a different class? You're in my class.
No, I'm not.
Oh, you're not in my class. What did your instructor do? It looks rather different.
C on one side, my C2 plus on the other.
That's fine, yeah. You could put a neutral and a 2 plus here, as long as they sum up to plus 2. That's fine. Yeah, that's no problem, if that's what you're asking.
Would it just be like C on one side and C on the other side?
Eh? Or whose class are you in?
Doctors?
Okay, he's into that sometimes. I don't do that ever, but I have seen him doing neutrals on both sides, but a 2 plus in the middle. I'm not sure why, but he does do that. Huh? If that's what he taught, he's asking is the way correct. If that's what he taught, then we would need to accept both answers. Yeah. Okay. I think we didn't get very far at all, but I'm going to have to pause there. We got this, this. All right, that's all we could do. For those of you who want to go now, this is a good time to leave. And then people have specific questions. Stick around. In about a minute, we'll resume.